The problems in section 12.6 are going to be difficult only because they are going to start off as word problems. The actual solution method using calculus will be easy in most cases, but most people kind of freak out when they see word problems. So hopefully we'll be able to at least be able to address the couple of different types that are here, and without freaking out too much. This problem I'm illustrating here has to do with maximizing revenue and maximizing profit. So there's two different questions. The A part is maximizing revenue. So we've already done problems like this. In particular, on the last test, there was a problem like this. So if we're trying to maximize revenue, that means we want a revenue function. And we know that revenue is price times number of objects sold. So here the price is 600 minus 0.1x times number sold is x. So our revenue function, if I multiply that through, will be 600x minus 0.1x squared. So to find the maximum, we know that we want to try to find the critical values, and then if we have several critical values, we might want to find natural endpoints and find the y-coordinates of the endpoints and the critical values. In this case, though, we're going to find that there's only one critical value, and the function is concave down always. So when that happens, we know from section 12.5 that if there's only one critical value and the graph is concave down everywhere, then that one critical value must be at a local maximum of the function. So with this should work as long as there's only one critical value. So if we do this, the derivative of 600x is 600. The derivative of 0.1x squared is 0.2x. So to find critical values, I'm setting this equal to 0 and then solving for x. So I'll have 600 is equal to 0.2x. And that means that x is 600 over 0.2, which is the same thing as 600, so that's 3,000. So these are phones, so x represents the number of phones that we're selling, so that's 3,000 phones. So that is the production level that we should have, so 3,000 phones. And they ask us here for the price. Well, if you wanted the price at a level of what price you should charge in order to sell 3,000 phones, that's going to use this equation. Right? So if you remember what each equation stands for, you'll be in good shape. So according to that equation, P should be 600 minus 0.1 times the number of phones that we're trying to sell, so times 3,000. And so that's 300 phones. I'm sorry, $300. Right, prices in dollars. The second part of the problem would be to try to maximize the profit. They do ask here, what is the maximum weekly revenue? We haven't answered that yet because this is weekly revenue. So if I want to know what that maximum weekly revenue is, I need to know how much revenue do I expect from selling 3,000. When x is 3,000, what's the revenue? And so that's putting 3,000 in for x into this thing. And so that's, well, I'll let you figure that out. That's got a lot of zeros on it. The profit, on the other hand, if I'm trying to maximize profit, then I need to start off with a profit function. And we know that profit is revenue minus cost. And so to do this, I'm going to have to find critical values for profit, which means I need to find the derivative of profit. The derivative of profit is the derivative of revenue minus the derivative of cost. And the reason I'm thinking of it that way is because I already calculated the marginal revenue. I already did that problem. So rather than do it again, I can just copy down my answer for marginal revenue that I had above. So marginal revenue is 600 minus 0.2x. And then I have to subtract marginal cost. Marginal cost, remember, is the derivative of the cost function. Well, the cost function is here, and so that's a very simple equation. The derivative of C, oops, I have a pen that writes, the marginal cost, we can see, is just 135. There's not even an x in there. So back down here, my marginal cost is 135. So marginal profit is 600 minus 135, which is 465 minus 0.2x. And again, setting that equal to 0 means that we'll have x is 465 over 0.2, which if we do the arithmetic there, that's 2325, and again, that's phones. So that's the level of phone sales that will maximize our profit, as opposed to the 3,000 phones that would maximize just our revenue. And again, for either of those answers, we could figure out the price point for that production level. We could figure out the profit or revenue at that production level. So once we have that value of x, then we can answer any of the questions. Okay, another problem in here is along the same lines, but actually has us working with something that's a little more realistic, which is sort of data that you would get from a market survey. And we did some problems like this before with talking about hot dog sales at a stadium, and some people were able to do it and some people weren't. What happens here is that we have to find the price-demand equation to start with. So up here, we were given the price-demand equation, this guy. That's just a line. It's the equation of a line. If we're working from data, we have to find that equation of the line ourselves. So let's imagine that we had data that was given graphically, and what I like to do is use x as the horizontal axis, and x should be the number of items. So this should be the number of, in this case, sandwiches. And if I'm trying to find the price-demand equation, then I should be looking for price, and so that's going to be dollars. So the vertical axis is going to be in price, or going to be in dollars. This piece of information that we're given to start with, 480 sandwiches cost $4 each, gives us a point on this line. So there's going to be a point here that has x equal 480 and p equal 4. So that would be the point 480, 4. A 10-cent reduction of price would take us down to $3.90 for price, and it says that 4 more sandwiches would be sold. So 40 more sandwiches would be a level of 420 sandwiches at a price of $3.90. That's $3.90. So if we keep following that pattern, that every 10-cent reduction is a 40 sandwich increase, then we'll have a straight line. So there's going to be a line that goes through these points, and so the price-demand equation is just going to be the equation of that line. How do I find that? Well, I just find first the slope. The slope between these 2 points, it's rise over run, so I will have 4 minus 3.9 is the difference in the y-coordinates of those points, and then 480 minus 520 is the corresponding change in x. That's just the change in y over the change in x. Where here, the y-axis, of course, I mean the vertical, which is p. So this is 0.1 over negative 40. So that is negative 1 over 400. So that's my slope. So therefore, the equation of my line, I would fill in this point-slope form, like we've always done. I have a couple of blanks to fill in here. I have p minus something equals slope times x minus something, and the something should just be a point on the line. So this is the easiest point to work with, the original one that we were given. So that's the point where x is 480, so x minus 480, and p was 4. So our price-demand equation is negative 1/400th x, negative 1/400 times minus 480 is going to be positive 480 over 400, which is positive 6/5 if you work it out on your calculator. And then this minus 4, I'm going to add 4 to both sides so that I have this over here. And so that's minus 1/400x. Uh, 4 is 25th, so that's 26/5. So that's my price-demand equation. I'm not going to worry about the rest of the problem because the rest of the problem is exactly like the one we just did. We're trying to maximize revenue, so the next step would be setting up revenue is price times number sold, and the price, of course, is given by the price-demand equation. So everything else about that problem is exactly the same as before. The only difference here is that we're using marketing survey data to come up with our price-demand equation instead of, in this problem, having that price-demand equation given to us.